Hello everybody, and welcome to this chapter 5 of our nanoelectronics course. Today we're going to talk about conduction mechanisms. Now we have had the chance to see up until now that devices we had a look at under certain biasing conditions, they will pass some current through, which can be large, small, and so on. But the question now is what type of mechanisms could be involved when current is passing through a device. So we'll try to have a look at this, and in order to organize a little bit our exploration, we will categorize these conduction mechanisms in two big classes. And the first one is the so-called bulk limited conduction mechanisms, and the second one is the electrode limited. So when we talk about bulk limited, we mean all those mechanisms where is the bulk that dominates the scene, that dominates what happens. Here we will look at two main ones, that is the Poole-Frenkel conduction mechanism and the hopping one. The other category is the electrode limited conduction mechanisms, where in this case instead is the electrode that is very important, or maybe the relative position of the Fermi level of the electrode as compared to the semiconductor or the insulator that the electrode is in contact with. And in this direction we will look at tunneling. There are several different mechanisms we will have a look at, so direct tunneling, Fowler-Nordheim, and so on and so forth. And then we will also have a look at the Schottky emission that we've mentioned already some time ago. So let us start with electrode limited mechanisms. And the first one to look at is obviously tunneling. We've already mentioned some time ago when we had a look at nanoscale physics, the two fundamental ones, let's say, is direct tunneling and Fowler-Nordheim tunneling. We've already said that direct tunneling is characterized by the fact that the electrons, the charge carriers, tunnel through a barrier that is square or trapezoidal. So we are in this situation here. In this case, it is extremely hard to find an analytical expression that relates the current density with the electric field applied across our device. But what we can say is for sure is that this tunneling current is exponentially dependent from the tunneling distance A, and most importantly, there is no temperature dependence. This is a fundamental characteristic that relates to any tunneling phenomena. Also for Fowler-Nordheim, we can, where shall remember, we have in this case tunneling through a triangular barrier now, as shown here. Well, in this case it is possible to find through some approximations and assumptions an analytical expression that relates J to the electric field in the dielectric material. Sometimes we will indicate that as EOX also, the electric field in the oxide. And so, but also in this case, what we have to point out is that again there is no dependence on the temperature. Now, in the case of the Fowler-Nordheim tunneling, we can arrange a little bit better the equation just to understand a bit more clearly where are the important terms. So we can write the equation that relates J and E, the electric field, in this way here. So J is A time the electric field squared time an exponential that depends effectively over the 1 over Eox. The constants A and B are given here, and as you can see, both A and B depend on phi B, which is the barrier, where, remember, the barrier was given here, and we can go back to the previous diagram where in this formula here the barrier was phi 1. So Q phi B is the barrier now, and in these plots down here we can see an example obtained from an MOS device. So we see here the tunneling current J and versus the gate bias applied on the metal gate. So our MOS device is the band diagram is represented here, metal, an oxide that in this case was silicon dioxide, and a silicon semiconductor. And so for VG negative, the band diagram looks like the one that I've indicated here. And so we are, when VG is negative, we are pushing upward the metal gate side, and so we are effectively promoting the injection of electrons from the metal into the semiconductor, into the conduction band of the semiconductor. And so this part here of the JV characteristic is indicating that at a certain point we have Fowler-Nordheim tunneling. So what you can see is that here the current is increasing exponentially as we keep moving into more negative VG values. And this is exactly Fowler-Nordheim tunneling. Something similar happens when we go to positive VG values. So in this case, we are when we apply a positive VG on the metal gate, the band diagram has to be modified by pushing downward now the metal side, and so we end up with something similar to this diagram here. And so we are effectively in this case promoting the injection of electrons from the conduction band of the silicon side into the metal, and so the resulting current we would get is the one depicted here with the green. And so again we see here this exponential increasing curve that corresponds to Fowler-Nordheim tunneling taking place there. These two portions of the Fowler-Nordheim tunneling taking place, they are not exactly the same. As you can see, this bit here of the curve and this bit here of the curve, they are not exactly the same. And the reason is because the characteristics of the barrier that the electrons are going through is different in the two cases. In one case, the electrons see the barrier from the metal and oxide interface. So that's the barrier that the electrons see. So the electrons in this case see the barrier arising from the contact between the metal and the oxide. While in the other case, the barriers that the electrons see is the barrier arising from the contact between the semiconductor and the oxide. And so these two cases are not obviously necessarily perfectly the same. So we should expect that these two Fowler-Nordheim characteristic for positive and negative biases, it will not be exactly the same. Now, in order to highlight whether we have Fowler-Nordheim tunneling or not, what we have to do is a special plot that is highlighted here in this plot. So if we plot the on a logarithmic scale j over e squared, and on the abscissa we put the inverse of the electric field. Please remember that this is the electric field in the oxide where the Fowler-Nordheim tunneling is taking place. I'm highlighting this point because we should remember that if there is a semiconductor involved somewhere, we should in principle take into consideration also the surface potential of that semiconductor in any given biasing condition. So we know that there is a little voltage drop also in the semiconductor. So in principle, we should take it in consideration before we plot these curves, because the electric field that we've put here is the electric field in the oxide. Anyway, once we do this plot, straight lines should appear. In this case, we can clearly see these straight lines. Obviously, there are parts that they do not follow the straight line, and this is because obviously they refer to the regions where the current was still very small and we still were not into the Fowler-Nordheim regime. Now, the reason why this plot allows us to highlight the presence of the Fowler-Nordheim mechanism is very simple, obviously, and comes from the analytical expression we found previously regarding the Fowler-Nordheim tunneling current. So if we take this expression here and we divide both sides by E ox squared and then calculate the logarithm on both sides, so basically we are calculating this quantity, we can easily see that this is equal to the logarithm of A minus this term here. So if we call now this quantity our ordinate y, and we call this quantity our abscissa x, we can clearly see that there is a linear relationship between these two quantities. ln A now is the intercept of this straight line, and minus b is the slope. And so we can now plot this data, and we should get a straight line, as we said, and the slope is minus b. So by doing this plot, we can calculate minus b, the quantity minus b, that if we go back to our previous slide, is actually related to phi b. So we can, by doing this special plot, we can not only demonstrate that we have a Fowler-Nordheim tunneling, but we can also, by estimating b, we can then try to estimate phi b. That is the barrier seen by the electrons that are tunneling via Fowler-Nordheim mechanism. Here is some a very simple exercise for you to go through. So have a look at this. I would like to let you think about this, and we can discuss then next time we meet. Another case where we may have tunneling involved is when we are dealing with a stack of dielectric materials. And in this case, what we may come across is this modified Fowler-Nordheim tunneling. So this type of mechanism is actually a combination of direct tunneling and Fowler-Nordheim, and as I said, is particularly evident and must be taken into account when we are dealing with dielectric stacks. And effectively what is happening is very briefly shown in this band diagram here, which represents a dielectric stack made of hafnium dioxide and silicon dioxide. So in very few words, what we are talking about here is that in this biasing condition represented in this diagram here, where we are effectively imagining to apply a negative bias to the silicon side so that the silicon side is pushed upward, as you can see, and so electrons should start tunneling through the insulators. But we call this modified Fowler-Nordheim because effectively we have the electrons tunneling through a trapezoidal barrier that is represented by the first insulator, in this case silicon dioxide, and then though a triangular barrier represented by the second insulator. So it's a combination of direct tunneling through the first one and Fowler-Nordheim tunneling through the second one. Okay, we will come back later when we will discuss non-volatile memories and transistors. We will come back later to this point of dielectric stacks and what it exactly means, but I would like to point out first of all here that the electric field in the silicon dioxide and the electric field in the hafnium dioxide are different. This is related to the fact that these two materials have different dielectric constant, relative dielectric constant. And also I would like you to note that these two materials have very different band gap. Just to be clear on what this device looks like, so in this diagram in this schematic, I've tried to summarize the details of this dielectric stack. So we have a silicon substrate, and then we have a silicon dioxide insulating layer, a hafnium dioxide insulating layer on top, and then our metal. And just so you know, the silicon dioxide layer has a relative dielectric constant K of 3.9 and a band gap of roughly 9 eV. On the other hand, hafnium dioxide has a much higher K value, 25, so it falls into the category of material that we will call high K materials. Generally, we call high K anything that has a dielectric constant higher than the silicon dioxide one. And but the band gap is much smaller, as you can see, so it's 6 eV. Okay, and the reason why in the previous diagram the electric field, I said that the electric field is different in the two insulators, which I realize that the electric field is different is because, as you should know by now, the band bending here is different. So the slope is different. So this means that there is a difference in electric fields. Now, the reason why there is this difference in electric fields is because of a very simple electrostatic rule, or equation if you like, is that at the interface between two materials, electromagnetism requires that this equation is true. So in this case, at the interface between this insulator, silicon dioxide, and the hafnium dioxide, the product of the relative dielectric constant times the electric field at the interface must be equal. And so it's basically this equation that from this equation we can then realize that the electric field in the silicon dioxide is different from the electric field in the hafnium dioxide, and the factor by which they differ is actually related to the ratio between the dielectric constants. So in our case, this ratio is roughly 6. And so we should expect that the difference in slope between these two materials should be, in ideal circumstances, around 6. So going back to modified Fowler-Nordheim, so when we are dealing with a dielectric stack, the question is, okay, what mechanism will I see or will be at play at which voltage? So this diagram here that I've made is exactly there to help you realize what should be dominant at which voltage values. So if I have my dielectric stack as the one that I've shown you here, so we have our metal, hafnium dioxide, and then silicon dioxide, and then finally the semiconductor. Then, as we start applying voltage, let us imagine obviously the voltage is applied to the metal gate in this case. So I should expect that initially the electrons should be only tunneling through the entire stack. So I should expect modified Fowler-Nordheim tunneling to be at play. So for voltages, up to these values. Then if I increase further the voltage, so let's say up to these values, I should expect direct tunneling. So because I'm effectively pushing downward the metal so much that now the electrons only see the silicon dioxide. They don't see anymore any barrier coming from the hafnium dioxide. And if I keep increasing the voltage now, we will at a certain point enter the Fowler-Nordheim regime, and the Fowler-Nordheim regime would be through the silicon dioxide. So the JV characteristic that I will see could be analyzed in 3 regions, most probably. So the first one at very low bias due to modified Fowler-Nordheim. The second one could be most probably direct tunneling, and the high voltage one could be probably related to Fowler-Nordheim. In presence of traps, tunneling could be also at play with another more complicated mechanism that goes under the name of trap-assisted tunneling. And to understand what it is, we could have a look at this energy diagram here. And very simply, what is happening is that electrons from, for example, our semiconductor tunnel to one trap site, and then from the trap site tunnel further into the conduction band of the insulator present. So in this case, we are assuming that we are using, for example, again a dielectric stack made of silicon dioxide and another insulator, silicon nitride. So trap-assisted tunneling is a mechanism where traps become involved in the conduction process. They assist the tunneling process, as we've just explained. Remember that traps are in general capable also of keeping this charge. And we know now that if charge is located somewhere within an insulator, this causes changes into the energy diagram. So we should understand that this is a dynamic process. Charges go in, are trapped, and then are released, and so it becomes quite complex when you start taking into account also the effects that the charge trapping has on the energy diagram, and so it's extremely complicated to if someone wanted to find analytical expression for this type of phenomena, but they are generally modeled, and the simulation tools are created in order to try and verify whether in a given device trap assist tunneling could be a play. Tunneling is obviously a very fundamental phenomenon, as we've said already, I guess, many times, and there are several very important applications where tunneling has been used. The first one, and probably the most famous one, is the tunnel diode, which was invented by Esaki. And the second one is the scanning tunneling microscope, which is used to characterize the surface of a sample at atomic level. The scanning tunneling microscope works on a relatively simple principle. We know that the tunneling current is exponentially dependent from the tunneling distance. So if we imagine to have a tip like that, extremely sharp, atomically sharp, I would say, and we imagine to have a surface that is rough, then if we could keep the tip at constant distance from the surface in such a way that the tunneling current is kept constant, then we could use the motion of the tip over this surface as we scan it to effectively recreate a profile of that surface. So the principle is extremely simple, but very accurate, because as we said, the tunneling current is extremely sensible to any changes in the distance. The tunneling distance is exponentially dependent to the tunneling distance, and so the tunnel diode is actually another. Is very interesting, and we shall have a look at it, as we briefly had a look some time ago to PN junction. So the tunnel diode is actually a heavily doped PN junction, and so let us have a quick look at how it operates. So these diagrams here should explain very clearly the principle, and so first of all, we need to have two highly doped P and N sides, so P plus and N plus. The fact that they are heavily doped means that the semiconductors are effectively degenerate. This means that we cannot talk anymore of, for example, silicon with few impurities. Now there are really a lot of impurities. And so this effectively means, if you remember, that what we've said some time ago, that in a degenerate semiconductor, effectively the Fermi level is either very close to the conduction band or the valence band, or even beyond them. So, for example, in this case, in the diagram that is in the energy diagram here, we can actually see that these two sides are so doped that actually the Fermi level is, in this case, is within the valence band, and in this case is actually within the conduction band. So this effectively means that in equilibrium, with no external bias applied, the levels in the valence band that are filled are up to this point. And in the conduction band, the levels that on the end side, the levels that are filled are up to this point. If we now have a look to understand, what type of current we should expect for which bias, we can have a look now to this sequence of diagrams here. So these are drawn with the corresponding IV. So when we are applying a slightly negative bias, the current is negative through the PN junction, but is quite high. And the reason is that the diagram should look something like that. You can see that now the field states are down here. So the states that are filled in this point, they can happily tunnel into the conduction band. And so that's why we have this very high current here. Now, when we move to zero bias, we are in the equilibrium situation that we've seen previously. There is no available states, obviously, where electrons can tunnel to, and so there is no current, obviously. But then if we now keep increasing a little bit the voltage, so we move to a slightly positive bias, then we see that obviously by applying a positive bias to the PN junction, what we are effectively doing is we are either pushing upward the N side or pushing downward the P side. In either case, in both cases, what happens is that now the field states that are here now see in front of them empty states, and they can tunnel through. So if we keep going, if we keep moving, if we keep increasing the voltage now, some states, at least the top one, will not be able anymore to see available states on the other side. And this is the situation depicted here. So if we are increasing a bit more, the current will decrease because all these states that are above, all these states that are from here to here, they cannot tunnel anymore. So there is a decrease in the number of available states that can effectively tunnel. This means the current is decreasing. And that's why we understand now that the characteristic, the IV characteristic of a tunnel diode goes through a maximum, a local maximum. If we keep increasing the voltage further, then effectively we prevent any other tunneling situation. The only thing that can happen is that some electrons acquire enough energy, thermal energy, to overcome the barrier existing between the PN junction due to the depletion region, and so we know how it goes. Then it becomes a standard PN junction effectively. Oh, please note that the tunneling we are talking about here between the valence band and the conduction band requires that energy and momentum must be conserved. So this is very important for the tunneling process to take place. Also, one question we should ask ourselves is the electrons that from here tunnel into the conduction band of the end side, what barrier do they see in front of them? Well, the answer is relatively simple here, because for those electrons to tunnel, they effectively have to find themselves in the conduction band, which means that the barrier these electrons are seeing is effectively this one here. So it is effectively the band gap of the material that defines the height of the barrier where the FM tunneling is taking place. Before we move to our next conduction mechanism, let me just spend a few words about what we said previously, that for the tunneling process to take place, we need to make sure that energy and momentum is conserved during the process. And if you see here, there is the statement that I've put that this means that effectively it is better to use direct bandgap semiconductors like germanium, indium arsenide, and so on and so forth. So let me just remind you what direct and indirect bandgap semiconductor means, and which are the implications then in terms of tunneling in our, for example, tunneling diode. So if you go back at the beginning of our slides, I think chapter 2, I did put, we do have there the band diagram of, I think, germanium. And there what you notice is that if you look at this band diagram, this is K, the wave vector, and, the energy, you will notice that the valence band and the conduction band are effectively aligned. So the minimum of the conduction band is aligned with the maximum of the valence band. So this represents the characteristic case of a direct, what we would call a direct semiconductor. And this is true for example, germanium, indium arsenide, and so on. On the other hand, when there is no alignment between the two bands, we will then say that we are in the case of an indirect semiconductor. So in this case, for example, there is clearly a mismatch in the position of the minimum of the conduction band and the maximum of the valence band. So this would be an example of indirect semiconductors. And this is typically the case of silicon. So as you can see here, there is a mismatch in terms of momentum between the maximum of the valence band and the minimum of the conduction band. So effectively, this means, going back to the tunneling process, that when our electrons from the valence band tunnel into the conduction band on the n side, then energy is conserved by the fact that the electrons tunnel into states that have the same energy of the injected electron. But momentum also must be conserved, which means that if this semiconductor used for this p-n junction was silicon, this would imply that in the n side a phonon must be involved to accommodate the change in momentum that is required for that electron to suddenly occupy a state into the conduction band. This makes the tunneling process much more, much less probable, because we need to find a phonon that within the crystal that has exactly that K that is required for the process to happen. On the other hand, in the case of a direct semiconductor, the process would be much simpler, because we are going from, if you consider the topmost level in the valence band to the bottommost level in the conduction band, these have effectively the same momentum k, which is 0 in this case. And so we understand that there is no need for a phonon to be involved, and so this means that effectively momentum is conserved, and so we only need to require that the energy is conserved. So we only need to wait for the right level to be available, as we said previously. Let us consider now another electrode-limited conduction mechanism, which is the Schottky emission. We have briefly mentioned this some time ago, as I said previously, when we were dealing with metal semiconductor contacts. And the Schottky emission is something that reminds really a lot the thermionic emission. So it's a thermal process, if you like, and but it is also field activated, and we will see this in a moment. So the thermionic emission is a process that can be described through this formula here. So this is the formula that provides how much current we should expect when the material, the electrode, the metal, is at a certain temperature T. And Pm is the what we would call the work function of the metal. So it's the energy required for an electron on that metal to effectively become free from the metal. So is emitted from the metal into the vacuum. So this is what we call thermionic emission. Now, in the case of a metal semiconductor system, what we could expect to happen is something similar to the thermionic emission, also temperature activated, but this time the barrier would be smaller. So if we imagine to have a metal semiconductor system, so this is our metal and this is our semiconductor here, this is the conduction band. This one here is the conduction band of our metal. So the electrons from the metal could potentially acquire enough thermal energy to move into the conduction band of the semiconductor, and so become in a way free from the metal. And the barrier they have to overcome is phi b, which is the energy mismatch between conduction band and Fermi level of the metal. So this would give rise to some current passing through this metal semiconductor device, and so the current, the relation maybe describing the current as a function of temperature and electric field is this one here. So if we compare where A, remember, is this constant down here, CRD is a constant, that is this number here. Now if we compare this formula with the thermionic one, we realize that A T squared effectively represents the thermionic term. So in addition, we have this bit here effectively, this exponential containing the electric field. So this is the only new bit that we have added, and this is effectively the term that adds this electric field activated mechanism, and that differentiates the Schottky emission from the thermionic emission. So what this term is telling us is that there is the electric field, as if we increase the electric field, this current is effectively increasing exponentially. That's what is effectively telling us. But still, it retains also a strong temperature dependence. Now, please note that for Schottky emission to take place effectively, this phi b, the barrier between the semiconductor and the metal, has to be generally small. Otherwise, other mechanisms that we will discuss or we have already discussed may be more dominant. So these barriers can be, let's say, of the order of, say, up to 1 eV or something like that. So below 1 eV. So let us try to understand where does this electric field dependence come from. Okay, so let us try to have a look at what is happening here. Now, this the term containing the electric field dependence in the previous formula providing the current density actually arises from what we call what is generally called the Schottky effect, and this is a purely electrostatic effect and arises from the realization that when you apply some electric field across your metal semiconductor contact, you have, yes, some band bending due to the electric field, which we know will cause some bending like that. So we have our, you can see the sloped shape of the conduction band in the semiconductor is due to the potential energy arising from the electric field, and this is why there is a slope there. So if it's due to the electric field, the external electric field we have applied. But now we need to realize though that if we place a charge here, for example a negative charge, this charge will create an induced charge in the metal, and this induced charge will carry some potential energy as well, will produce a potential energy. So that is represented here by this image potential energy, and we can demonstrate that this potential energy is effectively this shape here. So the real potential energy, and so which actually defines, if you like, the real shape of the bands near the interface with the metal, is actually, the total is actually this one here. So this whole Schottky effect is actually telling us that there is a barrier lowering that in this case is represented by this potential, electrostatic potential delta phi, or if you like, this potential energy Q delta phi, that is always at play when there is some charge near the metal semiconductor interface that we need to take into account. And so it is this barrier lowering that is originating the term that we've seen previously. So the higher the electric field, the higher the barrier lowering we see. So if we look at this formula here, we can see that the barrier lowering delta phi depends on the actual external electric field we have applied. So as you can see, the higher the electric field, the larger delta phi. So this means that the higher the external field we apply, the lower the barrier becomes, seen by the electrons that are in the metal. So the electrons that are here and want to jump over, as we said, the Schottky emission is basically electrons that want to jump over the barrier. So now we understand through this mechanism that the larger the electric field, the lower the barrier becomes. And so the easier would be for the electron to jump over this barrier. And this justifies although qualitatively, the shape that we see here in this conduction mechanism that relates J to the electric field. So we should expect that the electric field causes an exponential increase in the current we see through this metal semiconductor contact. And this is visualized here in this diagram. So as you can see, the more in this case, we are assuming that the metal is at potential equal 0, and we are applying an increasingly positive bias to the semiconductor. So we are pushing downward, you see the semiconductor side, and correspondingly you can see that the barrier seen by the electrons that want to jump over the barrier is coming down correspondingly. So, and this explains why I used previously the term that the Schottky emission is effectively one of the field-activated emissions we will see. Okay, so let us say that we have a device that we are testing in our lab. We measure. We apply some voltages across the device, we measure the current, we calculate J and the corresponding electric field, and we plot the data. How do we realize now whether the mechanism is a Schottky emission or not? So we have to, similar to what we have effectively said for the Fowler-Nordheim tunneling, what we have to do is to write in a more appropriate way this formula here. And what we should realize is that if we consider the quantity ln J over T squared, then effectively on the right hand side we can write the remaining terms as a constant, the intercept that is not depending on the bias, as you can see, but is depending on the temperature, plus a constant that depends on temperature and the dielectric constant of the semiconductor, whatever the material, and then our variable that is the electric field. So as you can see, this is now indicating basically a linear relationship between the quantity that I've called y and the quantity that I've called x. So if we plot this relationship, we should get a straight line. And if we fit these data, we should be able to calculate the slope and the intercept. Okay, well, now we would do this at a certain given temperature T. Now, from the intercept, in principle, the intercept represents this quantity here now. Now, if we imagine that we can calculate the CRD, from the value of the intercept we get at that given temperature, we could attempt to extract phi b. There is, though, a more accurate way to do that, and this effectively is the one shown here in this diagram. So what we do to have a more accurate estimate of phi b, of the barrier seen by the electrons that are jumping into the semiconductor, what we have to do is to actually do JE measurements at many temperatures, and so collect intercept values at different temperatures, and then we plot the intercept for each temperature we've used as a function of 1 over kT. This is because if we look at the intercept, this effectively is a linear relationship. If we look at phi b as a parameter, so 1 over kT here would be our variable, which we can call x. ln CRD is a constant, so this effectively is representing a straight line in this plot here. So if we plot the intercept at each temperature T which we measured and against 1 over kT, we should get a straight line with a negative slope, because we've seen that in the relationship there is a minus. And so the slope would be minus phi b. So this is a much more accurate way to test our data against the hypothesis that we have a Schottky emission. Obviously, if there is no straight line in these plots, it means that obviously it may not be Schottky emission. Let us have a look now at some examples of bulk limited conduction mechanisms. So the first one is the one we call hopping, and what happens is effectively what the term suggests. Charges, electrons move effectively hopping from one side to another. So imagine to be in a situation where we have our MOS device. So this is our metal oxide semiconductor system. And let us imagine that the insulator is not an ideal insulator, but has some bulk traps indicated by this dashed line here. So then what could happen is that the electrons from the metal side could, under appropriate biasing conditions like the one depicted here, we are assuming, for example, here that we've applied a negative potential on the side of the metal, well, electrons could hop into the closest trap site and then keep effectively hopping into the next one. Please note that this hopping process is actually a tunneling process, a direct tunneling process between one side and the other, until they eventually end up into the semiconductor. The analytical expression of the type of relationship between the current density and the electric field applied across the device that we should expect is actually this one here. So it is a J would be equal to a constant time the electric field applied across the oxide time an exponential term that depends from a constant, EA, and KT. Is thermal energy, where EA is something that is related to the barrier that the electrons have effectively to tunnel through. Again, how do we understand if we have a bunch of data of tunneling of current densities and corresponding electric field values from a given device? How do we understand, we check whether we have a hopping mechanism or not? Again, we have to devise a clever plot to do. In this case, it's quite simple. So this is our J-E relationship. So if we consider L and J, we can quickly realize that we can write the right-hand side then like that. So again, we have an intercept that is effectively a constant depending from the fundamental parameter of our device. And then ln EOX, the electric field in the oxide. So we should expect a slope 1 in a plot where the ordinate is L and J and the abscissa is ln eox. So the plot we should do is lnj versus ln eox, and we should expect the data to be fitted by a straight line with slope 1, and the intercept in this case would be related to, again, this quantity here, ln minus ea over kt. So in principle, we could calculate from using the intercept value from the fit we did. We could use that value at the temperature we made the measurement. We could potentially calculate EA. Again, similar to what we said previously regarding the Schottky emission, there is a more accurate way to do that, especially because we may not know this parameter A. So what we do, again, we do measurements of JE at different temperatures, on many temperatures, and so that we can get several values of the intercept at different temperatures that we plot. And again, if we look at the expression of the intercept, again we can see that if we call 1 over kt our variable x, let's say, then we should expect that the slope would be minus EA. And so, as you can see here, if we were to plot the intercept at different temperatures versus 1 over kt, we should expect a straight line with a slope that will give us straight away minus EA. This energy that we said we call the activation energy of the process. That, as we said, is related to the depth, if you like, of the trap sites. Okay, and related in a way to the hopping mechanism is another very important bulk limited conduction mechanism that goes under the name of Poole-Frenkel. Effectively, the Poole-Frenkel mechanism is combination of hopping and a Schottky emission. So as you can see, we can follow exactly the same example that we used previously. So same band diagram, same MOS device, but this time the electrons are effectively not tunneling into the next trap site, but are actually jumping over the barrier. So also Poole-Frenkel is an electric field activated thermal emission. Is similar to Schottky emission, but simply keeps going from trap site to trap site until the electron ends up into the semiconductor side, according to this diagram here. Oh, the relation between the current density and the electric field is shown in this formula here. You can probably realize that there are terms that remind the Schottky emission, as you can see here, and also the term that indicates the thermal process also that is involved. So this is also, as we said, a field activated emission, and the term phi1 that is represented there represents the depth of the trap. And again, as we did now several times, if we had a bunch of data of current densities obtained for certain electric field values applied across a device, how do we realize, or how do we check that we have a Poole-Frenkel mechanism? So here what we do is a plot of this type, lnj over Eox versus the square root of Eox. And indeed, if you do that, if you can see, you start from the expression, the relation we've seen previously. So if we calculate lnj over Eox, this can be, the right hand side can be transformed in this way, where lna is the intercept. Remember that in this case, ln is this whole term here, while the slope is represented by this term, which is very similar to the one we've seen for the Schottky emission. So there is the dielectric constant of the oxide material, the temperature involved, and the variable is the square root of Eox. So again, similarly to what we've done for the Schottky emission, we plot now our ordinate y lnj over Eox and our abscissa x, which is the square root of Eox, and we should check that we get a straight line. So the slope would give us information about this term, the carry information about the dielectric constant and the temperature, and the intercept again would give us information about lnc1 minus q over kt phi1. So again, it is better to actually to better estimate phi1. It is better to do measurements at different temperatures, so get several values of the intercept for different values of the temperature, and so plot then the intercept values that we got against 1 over kt, and in this way the slope would be minus q phi1, and so we can now calculate phi1 in this way. So using these techniques that I've shown you, we can not only identify that in our device there is one specific conduction mechanism that is dominating over the other, but we can also be quantitative and actually say a bit more. So for example, in the case of Poole-Frenkel, we can actually say, yeah, the traps that are involved in this process are actually located phi1 below the conduction band of the oxide, and so on and so forth. So it is in the process of investigating the properties of materials and devices. What I've just described you represents a fundamental process that a scientist goes through in order to understand what is going on and eventually optimize things so that the devices behave in the intended way. Okay, this concludes this chapter about conduction mechanisms. Thank you for listening, and I'll see you next time.